Hello, good afternoon, everyone. The first speaker of this session is John Aaronson from Tel Aviv University. He will be talking on inner functions revisited.
Oh, thanks for the introduction and thanks for the invitation and happy birthday. So I'm going to talk about inner functions, but I think before I start the slides, I should do, I don't know what you call it, a prologue, a preview, or a menu. Let's call it a menu. So if there's time, I reckon I'm going to do basics, inner function basics. Then there'll be something about ergodic theory. So an inner function, what's a basic? I mean, there'll be a definition there, but I have a transformation from, say, T, which is 0, 1, into itself. And you assume that it takes the T, so composition F goes to, so T of F, T takes the span. Okay, got the idea. So, span of T to the n bigger than 0, it preserves it. So this is under F goes to Ft, and phi of x is the character. So that's one definition of an inner function, sort of defined like that. So I'm going to do basics. We'll see that these are non-singular. We'll do some ergodic theory, and then there's going to be some probability theory, which involves in doing spectral gap for transfer operator. Then there'll be nice perturbations. By nice functions. Then there'll be limit theorems. Central limit theorem and local limit theorem. Okay, and there's one thing I'd like to say to start with. I'm going to kind of preview. Oh, that's a menu. This is a preview. That there is this kind of experience that the smoother a transformation is, the nicer the spectral theory for the transfer operator is. But here, the worse the inner function is, the better the spectral theory is. So that's one thing that's going to come out of this. Okay, so how do I, yeah. So an inner function. So you can see that I said that I preserved the linear span of characters, but that actually means I can write it as a power series inside the unit disk. So the formal definition is an analytic endomorphism of the unit disk, which preserves the boundary. So it's a bounded analytic function. There are radial limits almost surely, and these are on the boundary. So I get a transformation of the circle. So this is the restriction, we call that. So we have the same chi, and there's this thing you can talk about phi defined on the round circle, and you can talk about t defined on the unit interval. And it's more comfortable for me to stick with these tau defined on the unit interval. Okay. So the first thing is that actually it's non-singular with respect to Lebesgue measure. We didn't say that. We just said that it preserves the circle almost everywhere. And the reason is that there's this thing called Boole's formula. So we'll get to see why it's called Boole's formula later. But so if I take the Poisson measure centered at z, and I do the pullback with respect to tau, then this is the Poisson measure at phi of z. So the Poisson measure has density Poisson kernel, which we defined here. Okay, so the proof of that is basically Dirichlet theory, that you do Poisson integrals of, you take a function on the circle, you do a Poisson integral, you get a harmonic function, and then you take radial limits and you get back the original function. And so using the fact that I can consider these as these two guys. This guy I can consider as a Poisson integral in two different ways. If I look at the integral with respect to this measure, it's a Poisson integral centered at phi of z. But if I look at the radial limit there, then I get something with the limit of the original function composed with the inner function. So I get this formula. That's basically how it works. Although it's called Boole's formula, this is the mid-19th century. The first proof that I saw was by Nordgren in 1968. Okay, so I have transfer operator. So general idea of a transfer operator, given a non-singular transformation of a standard or probability space or a sigma finite measure space, you can define it like this. And in fact, I mean, you can define this, I mean, we talk about L infinity and L1, but you can define it whenever the integrals are defined for. So for example, for any two non-negative functions. The transformation is invariant. You have an invariant measure if the Radon-Nikodym derivative is invariant under the transfer operator. So for an inner function, then you have an invariant Poisson measure if and only if the center point inside the unit disk is a fixed point. So the point is here that if my inner function has a fixed point inside the unit disk, then there's an invariant probability. And the next thing I think says that this is going to tell me that this is the only way that this is true. There's something called the Donjois-Wolff theorem. So, okay, so if I have, there is such a thing as a one-to-one inner function, which we call a Möbius transformation. And these are kind of, in a certain sense, for our purposes, these will be degenerate. So we want something which is non-Möbius, and if I have a fixed point inside, then the derivative is necessarily less than 1. And every point, the iterates of the inner function tend to this Donjois-Wolff point inside. So we get as a corollary, so even if this is not true, now suppose, yeah, okay, the Donjois-Wolff theorem says what happens if there's no fixed point inside? Well, then there's an attracting fixed point on the boundary. And the fact that there's an attracting fixed point on the boundary means that the only way you can have an absolutely continuous invariant probability is if it's a Poisson measure with the Donjois-Wolff point inside. And a proof, well, I said that I should do one proof at least. So I suppose I take an absolutely continuous invariant probability and suppose that the Donjois-Wolff point is on the boundary. Look at the transfer operator of some Poisson distribution. So this is P phi n z, which is like that. And you can see that phi n z tends to delta. So this guy, if chi is not equal to delta, this guy will not tend to 0. To something else, and this tends to 0, so this goes to 0. And this prevents you, because if I had this will show that this will get the contradiction. So I apply the ergodic theorem to this, A epsilon, in fact, there shouldn't be an epsilon there. I take some A which kills an interval around the Donjois-Wolff point. And then I'm saying I've got some averages here. I want to look at the integral, there should be an integral here with respect to M. There's no integral sign. So on the one hand, according to the ergodic theorem, this should go to the integral of the conditional expectation with respect to the invariant sets. But on the other hand, by this, and I look at the sums of the transfer operators, I'm getting Chisaro averages of these guys, which are going to 0. So it gives me that the measure is equal to 0. So I'm sorry if you didn't get very much of that. You want to stop me? Yeah, by the way, if you feel that you're not getting something, just raise your hand, stop, shout, whatever. The Zoom people won't mind. Okay, so now we do some, now I'm getting into the ergodic theory bit. So conservative, ergodic, exact, these are the relevant properties. Wandering set for a non-singular transformation, it's some W. My wandering sets have positive measure, and it means that all the pullbacks are disjoint. So you call it dissipative if X is the union of wandering sets, which means that every set has a wandering subset. And then you can show that you're the union of accountably many wandering sets. Okay, you say it's conservative if there are no wandering sets. So for example, if there was an absolutely continuous invariant probability, then you couldn't have countably many disjoint sets of positive measure, because they would all have the same measure and sort of adds up to more than one. So equivalently, so this is a Hopf condition, transfer operator condition. We're interested in transfer operators for later. So this means that I have some L1 function which is positive, for example, a Poisson kernel, so that the sum of the iterates under the transfer operator should be infinite almost surely. If that's true for one, then it will be true for all. You call it ergodic if there are non-trivial invariant sets. And you call it exact if the tail field is trivial. Equivalently, if I look at the L1 norms of the transfer operators of L1 functions of integral 0, these go to 0. So what does that mean? That you take any two measures and you look at the difference of the two probability measures as transformed by the transfer operator, and you look at the total variation norm, this goes to 0. So the transfer operator squishes any two absolutely continuous probability measures together. And that's the same thing as having trivial tail. Okay, so here's a formula. This formula tells you that the geometry of L1, if you want, the action of the L1 is like hyperbolic distance. So this is some function of hyperbolic distance. I think hyperbolic distance this is the hyperbolic tangent of hyperbolic distance between z and omega. So that's a formula you can check out with using Boole's formula for Möbius transformations. And then you get for an inner function, the restriction is going to be exact if and only if any 2 points get squished together. And the reason is that this condition is exactly equivalent to the difference of the Poisson kernels being squished together. And differences of Poisson kernels generate all of L1 with integral 0. So that's a proof. I proved one thing. Okay. So as a corollary, you get that if it's not Möbius and it has a Don-Juan-Wolff point inside, then it's exact, because this guy tends to the Don-Juan-Wolff point, this guy tends to the Don-Juan-Wolff point. Therefore, look at that, goes to 0. Okay, so in general, there's a dichotomy. Either for any inner function which is non-Möbius, either you have this, in which case is exact, or there is an invariant, non-constant bounded analytic function for the inner function. So this proves that ergodic implies exact. Why? Because the radial limits of this would be a non-constant invariant function with a restriction. So now let's look at conservative. Conservative, we said, well, there's this transfer operator condition that I could take from my L1 function, the Poisson kernel, and that would be that it would be conservative if for some z, this sum would be infinite, but that's the same thing as this, exactly the same as that, the sum or all z. But that's a kind of Blaschke condition. So if you have that condition, you'd have too many, the function f would take the value phi n z too many times, and so it would have to be constant. So using Blaschke's theorem with this condition, conservative implies ergodic, and from the above, it implies exact. So the ergodic theory is pretty simple. And we want to go a bit further. So we want to look at transfer operators. So you want a spectral gap for a transfer operator. What does that mean? You find a smaller space which the transfer operator preserves. The transfer operator is pretty smooth, whereas the inner function doesn't have to be. So let's go into what are we into next? Oh, R2 plus, right. So I talked about inner functions on the disk, but I can transform this with a conformal map to, I don't know, any simply connected domain, or nice enough. And upper half plane is interesting. There things are simpler because you taking radial limits, so you can use the same formulae and things like that. So it's an analytic, as before, it's an analytic endomorphism of the upper half plane, so that you certainly have radial, what do you call it? Vertical limits as you go to the reals. And the idea is that almost surely these vertical limits are part of the real line. There's no imaginary part. So it's a non-singular transformation by Boole's formula. So now I'm taking the harmonic measures are now Cauchy distributions. So it takes a Cauchy measure to its image under the inner function. And this formula actually is for a rational function. This was one of the formulae in definite integration that Boole did in 1857. Yeah, I looked this up, a bit of history. So Boole's transformation is Tx equals x minus 1 over x. And this preserves the Lebesgue measure. And this was one of the formulae that Boole published in that paper. But apparently, according to Glaisher in a later paper, this was already known to Cauchy in the 1830s, this formula. So you could call this transformation Cauchy's transformation. So Boole generalized this for all rational functions and also did this slightly more complicated formula. Okay. So now there's a representation of inner functions. So if I have an inner function, the imaginary part is positive. It's a positive harmonic function. So it has the regular, I don't know, Herglotz representation. And then you take the real part. Well, the real part is an analytic conjugate. So it's the possible constant that you have to put in. And of course, there will be a certain mass at infinity. So we have the alpha tz at infinity. So alpha t is non-negative, beta t is real, and mu t is a measure on the reals. Because you want the vertical limits to be of the imaginary part to be 0 almost surely, this guy should be singular with respect to Lebesgue, because almost surely the vertical limits would be the Radon-Nikodym derivative with respect to Lebesgue. Okay, so if alpha, by taking limits, you can prove this formula about preserving Lebesgue measure. If alpha t is positive, then the mt minus 1 is 1 over alpha tm. So if alpha t is equal to 1, as in Boole's transformation, it preserves Lebesgue measure. This is saying that showing how to shift an inner function on the unit disk to an inner function on the upper half plane. There's this conformal map. You can choose the base point. Why do I want to choose the base point? Because if the Donjois-Wolff point, is on the boundary, then it is much more transparent or much easier to look at the transformation as on the upper half plane with the Donjois-Wolff point transformed to infinity. And so you get that alpha t is bigger than or equal to 1. Okay. So if alpha t is, so now we're talking about inner functions with Donjois-Wolff points on the boundary, and I've transferred everything to infinity. So if alpha t is bigger than 1, then it's dissipative, not ergodic. If alpha t is 1, then it's a measure-preserving transformation. It could be non-ergodic, it could be dissipative and exact, and it could be conservative. Conservative now is the strongest property because it implies everything else. So there are all kinds of examples that you want. Probably many that you don't want. Okay, so now we go back to, we're going to look at the structure of inner functions. And so we've got to think about non-singular endomorphisms of a Lebesgue space. So this is something that actually you could probably, you might be able to find this in Rochlin's work. So I called it endomorphisms of a Lebesgue space. So I have a Lebesgue space, Polish non-atomic probability space, transfer operator T hat, and then you have a transition kernel. So a transition kernel is a measurable function into measures on, so nu x is going to be a measure on the inverse fiber. And this is going to be positive linear functional and bounded continuous function. So X is a Polish space, remember. And X0 is a set of full measure. So these transition kernels exist by the disintegration theorem. So this is the basic theorem on which you with which you prove the existence of regular conditional probabilities on a standard space. There's a multiplicity property for a non-singular transformation. So the following are equivalent. You're countable to 1, which means that there's a countable partition mod 0 alpha, so that on each element of the partition, you are a measurable, invertible, non-singular map by non-singular from A onto TA. Another condition is forward non-singular. So we're talking about non-singular mt minus 1 is equivalent to m. Now we were talking about going forward. So what I want to say is that there's a set of full measure, so that if I take some subset of measure 0 of this set of full measure, then its forward image has measure 0. So those are two conditions. And the third condition is that nu x, this transitional kernel or the pre-image measure, is purely atomic for every x. So if it's countable to 1, you can imagine that nu x is on the countably concentrated on the countably many pre-images. Okay. So, yeah, okay. So if I have things like the shift of the Bernoulli shift, if I take the Bernoulli shift, the one-sided Bernoulli shift with continuous state space, the interval 0, 1, then that will not be, it will not be satisfy any of these conditions. Okay, multiplicity. So this kind of multiplicity, I mean, what's the size of the inverse branches? So Heinz showed that an inner function, or the restriction, is countable to 1 if and only if the derivatives have radial limits, non-trivial radial limits almost surely. So this is in particular, well, yeah, okay. So this means that you have what's called Karaterodori angular derivatives at almost every point. So another thing you know about it, if I look at the operator, the function for an inner function onto the pre-image measures, this is weak star continuous. So you could have an inner function which is not countable to 1, would be continuous to 1 almost everywhere, but still the transfer operator is weak star continuous and even better. Third thing is that for an inner function, the pre-image measures are always singular. Why? Because nu x of the Poisson kernel at Rx is Poisson kernel at phi of arc-C. And this goes to 0 as R goes to 1. And this goes to the Radon-Nikodym derivative because it's a Poisson integral. So Fraser showed there's a connection with, there's a Brazilian student of Manier, I think, in Marcos Fraser. So if I have an inner function which preserves 0, so 0 is a fixed point, the Lebesgue measure preserving transformation of the circle, then you have finite integral. If you have, finite entropy, you would expect that you would have Rochlin's formula, which in a certain sense, it would be the integral of the log of the Radon-Nikodym derivative, forward Radon-Nikodym derivative of the transformation. But we said that this is all the same by Heinz, so it's the same as that. So in fact, you get that finite entropy is exactly phi prime being Nevanliner. Nevanliner function, that's with this condition. This should be finite. Okay. So now we want nasty inner functions, things which are not countable to 1. So there's a result of Zaxman that if I have an inner function, I look at the pre-image measures and I have that this integral is infinite almost surely. So this is going to be something like the derivative according to the derivative phi primed at a point which maps onto 0. So this should be infinity for all points that map onto 0. Then not only is it bad, but all of the nu x's, the other fiber measures are all going to be non-atomic. purely non-atomic. So here's an example. I take mu in this kind of way, so it's a purely atomic measure, but it runs around the circle. Then support. And then this is going to be true. And so if I had an inner function like this, but I can define an inner function like this. So actually, Donahue did this. Inner functions were studied earlier in terms of operator theory. And for people like me and them, the untrained eye could not see inner functions in there. So this is much earlier than anything. So you have an inner function. There exists an inner function preserving zero so that nu x tau, the pre-image measures, are non-atomic for almost every x. And Zaxman was giving a construction of this because he didn't understand this paper either. So you define a function from the unit disk to the upper half plane by f of z is c plus, well, the kind of Poisson integral, if you want, of mu. So this is your mu. So then f0 is equal to 1. So now I take phi to be the mapping onto the unit disk. And this now is going to be inner with phi of 0 equal to 0 and phi 0 tau, nu 0 tau equal to this mu. Because that's how we defined it. So according to theorem, this is non-atomic for every x not equal to 0. Okay. So things can go bad. That was a question we were asking each other in the beginning, and some of the questions you can answer by looking on Google. Wikipedia didn't work, but Google did. Okay, so here's representations and singularities and multiplicities. So the representation theorem for in a function on the unit disk is the usual kind of multiplication representation. Blaschke product, so B is a Blaschke product. That's a product of things like this. The sharp function counts the multiplicity of the zero. So this is F is a collection of zeros. It satisfies this condition so that this product converges to something non-zero. And then it's going to be an inner function called a Blaschke product. And there'll be something left over. Even when I divide it by the Blaschke product given to me by all the zeros, I can still have a non-trivial inner function, which we call a singular inner function. And this has no zeros. And if I look at the log of 1 over the singular inner function, which is defined, then this is a positive harmonic function. So it has an integral like that. And also because it's inner, the radial limits are equal to 0 almost surely. So singular, sigma has to be singular. The set of singularities of an inner function is those points where it doesn't have analytic extension. So I guess the only inner functions with analytic extension over all the unit disk are the Blaschke products with a finite zero set. Otherwise, there could be an accumulation, there would be an accumulation point of zeros on the boundary. And there could possibly be some support of the representing measure of the singular inner function. So it's going to be a closed subset of the circle, the singular set. So when is it still nice? If the singular set has measure 0 on the circle, one-dimensional measure 0, then it's an interval map. So it's basically, there's a partition of T into open intervals so that on each interval, you're strictly increasing in real analytic interval map. So it's one way to be countable to 1. So the question arose. So maybe if you get bored, you can answer this question. Suppose you have a countable to 1 inner function. Yeah. So there's a measurable partition. Does that automatically mean that the singularity set has measure 0 and it's in fact an interval map? The partition that you have is into intervals. We couldn't answer that. Okay. So now we're getting on to any questions about representations and things like that. Okay, so now we're going on to spectral gaps and transfer functions. So where do I get a spectral gap? I mean, I start off with I have to have an adapted pair of Banach spaces. There'll be C, which is going to be, most times is L1. And I have L, which is going to be a smaller Banach space. So it could be bounded variation if I'm on the unit interval. It could be Lipschitz functions, Holder functions or something. So we're going to have slightly different one. But the idea is that L should be dense in C in the C norm. L closed bounded sets should be C compact. So in all of these examples, there's something like Alzella-Ascoli, which gives me that bounded sets in Lipschitz are compact, uniformly compact in the uniform topology, and therefore in L1. Okay, a Doeblin-Fortet operator. So this is with respect to an adapted pair. So I have a bounded linear operator from C to C, which is also a bounded linear operator on L. And for some kappa and R and H, and little r between 0 and 1, you have these equations. First of all, it's power bounded on C. Secondly, I have this two-norm inequality that P kappa of X in the L norm is less than or equal to, say, R times this guy, plus big R times the C norm. So I can, if I want to reduce the norm of the L norm of X, I apply P a certain amount of times. I've reduced it, but I have to pay something with an extra C norm. So that's a Doeblin-Fortet operator. Okay, so our guys are going to be, we're going to take C to be L2 of the circle, and KB is going to be the guys with exponentially convergent Fourier series. So this is sort of, if you like, you can think that this is, if I have a function on the circle which is real analytic, then it's going to be in some KB for B bigger than 1, some B bigger than 1. And this is, you can easily see that both of them are Hilbert spaces, although it's not relevant. But LP or L2 KB is an adapted pair. So that's where we're going to work. So here's the spectral gap theorem. So you have an inner function. It's not Möbius. It preserves 0. So it's a Lebesgue measure preserving restriction, exact and everything. And now I take some rho, which is bigger than the absolute value of the derivative at 0. So I'm saying that I get a spectral gap, and the spectral radius of the spectral gap, if you want, is rho. In this way. So tau to the n u minus the expectation of u, which is u hat 0. This is less than or equal to the B norm. So this is the KB norm. I'm multiplying, doing the L2 Fourier series norm, but weighting it with b to the power mod n. So this has a spectral gap like that. So it's less than or equal to m times rho to the n times norm of the B norm of u. So this is the inequality. So that's football is the spectral gap. Okay. So in particular, you get that it's a Doeblin-Fortet operator. You, for the kappa, you wait until m times rho to the n is smaller than 1. And then you say, okay, well, I'm going to say that it's less than or equal to this. The norm of this guy is less than or equal to the absolute value of the expectation, which is less than the L2 norm or something. And then I get the Doeblin-Fortet inequalities. So one thing we're getting here, there's a recent, how do you say, preprint from Rome, Batali Canistrari and Jane, Sakshi Jane, you might have known her here when she was a student in Delhi. You're looking at what's called the minimal spectral radius. So you want to look at the infimum, all the rows where the transfer operator supplies, satisfies football on some Banach space with the L norm bigger than or equal to the L1. So that's minimal spectral radius. And here you're getting that the R of phi is actually equal to the derivative. I mean, this one shows that this theorem tells me that for any rho bigger than absolute value of the derivative. So this tells me that Gothic R is less than or equal to the absolute value of the derivative. And to get that it's bigger, then, well, you can show that there's a z, so that p to the n of z to the 1 over n tends exactly to the right thing. And you can't get any smaller than that because of the Poisson kernels. So, okay, so whatever happens, I mean, we've got this kind of, we've calculated the, what you call it, the minimal spectral radius or something for operators of inner functions which are continuum to 1 if you want. So there is a kind of another work in progress, Oleg Ivry and Mariusz Urbanski, that they got spectral gaps for the transfer operators on more complex analytic defined spaces. There's something called the Dirichlet space, which is a Hilbert space where you take the, you're looking on the whole unit disk, and the Sobolev spaces on the circle. Okay, so that's spectral gaps. So now we get to perturbations. Okay, so you have a nice function. You want to do some probability theory on this kind of thing. So what do? Wait, yeah. Okay, let me talk a bit on the blackboard now. So the idea is that if I have Sn is equal to x1 plus x2 plus x to the n, and these are, oh no, shouldn't write on top, underneath, these are IIDs. And then I want to do probability theory. Well, I look at the characteristic function, these guys, and this is equal to e to the itx to the n. So this puts me in good shape, and I can prove most of the classical probability theory for independent random variables is proved using this. A lot of the probability theory for dynamical systems is trying to substitute this in a certain way. So what we're going to do is to fix up some kind of operator, and instead of having a characteristic function directly, because there's no independence here where we are, but we're going to get this kind of thing asymptotically as a kind of eigenvalue for a one-parameter family of operators. So this one-parameter family of operators is called the perturbation. And that's what we're going to do now. Wrong one. Yeah. Okay, so now I'm defining the perturbation. So I'm taking a function, a real valued function on the circle, which is measurable, and I'm defining pi z as an operator on L1, and pt. So pi z is defined by the transfer operator, what some people call it the twisted transfer operator. You take f, you multiply it by e to the z times psi, and then you do the transfer operator. Pt is when I take z equal to it. So you can see that if I'm going to get, if I get an eigenvalue for this or something, it's something like a characteristic function. So this is the analyticity of perturbation that we have here. So what I want to know is that the function, so given my phi, given my inner function or tau, and given my psi, the bounded measurable function, I want to know that these functions are smooth in z or in t. Okay? So what does that mean? So I'm saying that if psi is, psi should be in kb for b bigger than 1. And then I take a b which is smaller than big B. So there's big B, there's smaller b. And then I'm looking at the function z goes to pi of z as an operator, a bounded linear operator on the Banach space kb, the Hilbert space kb. And then I'm saying this is holomorphic, and the derivatives are what you think they are. So you're just deriving here. You just derive the inner function with respect to z, and that's what you get. These are the derivatives. So the way I prove it, I mean, the way one proves this, you have to do all kinds of standard analysis on KB. which would just fill up lots and lots of screens and lots of blackboards. So I'll spare you that. And then afterwards, okay, so what you've got now, you've injected a certain operators into this Banach algebra of operators here. Okay. So what do you know now? What do we know before? We knew from before that if z equals 0, then it's just the transfer operator. So we know the transfer operator has a spectral gap. So what we have is we've got an analytic function into, if I look at the pi t's, then I get a real analytic function defined on an interval containing 0 into the bounded linear operators on KB, and a 0 function is going to be spectral gap. So the point is that this extends. There's a general thing that inside the Banach algebra of bounded linear operators, the property of having a spectral gap is an open condition. If you're close enough to something having a spectral gap, you will also have a spectral gap. And so this comes about, this was noticed by Nagaev in 1957, who was doing this for Markov chains, and you get an eigenvalue. You get so what do you get? Small interval around 0, an analytic function. So what are these analytic functions? There's a projection. Projection is a function of the operator. So the operator was an analytic function. So the function, an analytic function of an analytic function is an analytic function. And so is the eigenvalue. So I'm getting this equation here. So the spectral gap, how do you say, persists in this kind of way. So the point is that this lambda function, this is going to be something like the characteristic function because it's going to be multiplicative. Okay, so now we want to know something about the expansion of the eigenvalues. So now we suppose we're in the same situation. So there's something called the asymptotic variance. So the first time I saw this applied to dynamical systems is this paper in '83 of Rousseau-Egel. Afterwards, there's a more famous paper of Ghosh and Hardy. And then things multiplied even more. So what happens is that should be a square. This should be expectation of psi n squared over n tends to what you call the asymptotic variance, that's sigma squared, and that's of this form. So G is going to be the sum of the psi, the transfer operators of psi, which converges because of the spectral gap that you get from the spectral gap. Okay. Sigma squared is 0 if and only if G is going to be measurable with respect to the T-1 of B. And this means that C itself was a co-boundary. So this is telling you when C was a co-boundary. So this is in general, yeah? If sigma squared is bigger than 0, then there's a bit of analysis you can do, and you get the expansion of the eigenvalue near 0, which is something like the expansion of the characteristic function near 0 if you have a centered L2 random variable. So therefore, you get the central limit theorem. So we look at this guy. This is what we want to look at. And this is expectation of P. There should be a power n there. Yeah. And so I apply the equation, the Nagaev spectral equation. So it looks like that. And this goes to the Fourier transform of the Gaussian distribution. So there's your CLT. Okay, so if sigma squared is positive, and you also know that the eigenvalue, absolute value of the eigenvalue is less than 1 for every t bigger than 0, this is kind of a periodicity thing, then we'll see below that you satisfy the local limit theorem, something like de Moivre-Laplace. Okay, so I should say that there are central limit theorems for, so first central limit theorem that we saw for inner functions was Nicolas Soler-Gilbert in 2020. So it's just for the inner function. So I'm looking at C, it's nth iterates of the inner function. Ivry-Urbanski did for a multiplier in the Sobolev space. So what's aperiodic? So periodic if there's if you compose with a character and you're cohomologous to a constant. Okay. So e to the it psi is lambda times a coboundary, a multiplicative coboundary, and aperiodic otherwise. So there's no loss of generality in G being equal to 1 in these things. I don't know why I put that there. So now we're saying that C is periodic if and only if there exists T, so that G, the transfer function, is an eigenvalue of the twisted transfer operator at T, or a characteristic function operator. So this is using basically, it's a standard thing. I mean, you just have to remember that conditional expectation is an orthogonal projection. So if you're aperiodic, there's no eigenvalues of PT of absolute value 1, any of them. So I take lambda of T, I use the spectral gap thing, and this is less than or equal to this is the spectral radius, right? So the spectral radius is less than 1. In fact, it would be, yeah. So now this is eigenvalue rigidity problem. Suppose you had an eigenfunction. Suppose you had an eigenfunction in L1. Well, then it would have to be in your space of analytic function. It would have to be real analytic. Have to be analytic. Yeah, have to be in KB. And the reason is, well, we've got Doeblin-Fortet operators, and there's kind of Yoshida-Ergodic theorem, which tells me that if I have a function, if I have a element in the small Banach space, the Chisaro averages of the operator with it converge in the small norm, so that's the norm of the large Banach space, to a limit which happens to be in the small space. And then you can approximate this guy by things like that, and then you get eventually that this itself is a limit of things in the small space, so it itself will be in the small space. The small space for us is KB. The big space is L1 or L2, whatever. Like we had in the adapted pair. Okay, so now the idea is that as soon as you have something with a singularity, then it's not a coboundary. And so as soon as your function is in KB and not constant, then C is aperiodic. So actually the proof is quite simple. I mean, what you have to do, so you're looking at P, T, what are we saying? F is equal to lambda F. And this is the same as, what are we saying? E to the I, T, C, F, T is equal to lambda F. So if I look at that equation, that is analytic. That is analytic. The only possibility of not being analytic is this guy. But these guys, this F itself is real analytic. So even at the point of zero derivative, there's a continuous inverse branch. So I'm getting a contradiction. I'm getting a discontinuity there. In fact, the proof is slightly longer because things are almost everywhere, and then you have to do some measure theory for that. But that's on one leg, that's the proof. So as a corollary, we get local limit theorem. So this is the de Moivre-Laplace. Root n times, it's a conditional local limit theorem, tau hat n of the set where Cn is equal to Kn is contained in a translate of an interval I by Kn. I'm assuming that Kn doesn't go crazy, so everything's fixed. Kn divided by sigma root n tends to kappa. Kappa is some real number. These can be real. I don't know why I put Z. Okay. And then you're getting the estimate, this estimate. This is the limit. And the reason, okay, so what we've done up until now means that I can prove this using the method of Breiman. So that's, I think, my last slide. So it's a Fourier method of proof. And this was stated for IIDs in Leo Breiman's book. So you choose an H. You want H to be non-negative. In fact, positive if you want, but it can be done like that as well. So you want it to be non-negative, and the Fourier transform should be with compact support. I'll give you an exercise. It's a nice exercise for how to do that. So now so epsilon, if you remember, there was we had the Nagaev perturbation property. I had a little interval which mapped into the operators analytically. So that interval was epsilon. Theta is the spectral gap of, or the error term. By aperiodicity, I can find some eta less than 1, so that the supremum of the eigenvalue, or the sup of the eigenvalue, when I'm bigger than epsilon, less than n, m is less than 1. So this is eta. So now I look at this guy. So instead of taking, what do we have? Yeah, instead of taking the indicator function, so this is kind of indicator function of kn plus I, I'm taking h to be a smooth function like that. So I'm evaluating this, and I'm looking at h as a Fourier integral, and then I'm exchanging tau hat to the n with the integral, and this is what I get. So an integral of the Pnx of function 1, and I'm taking a Fourier transform of this when weighted by Fourier transform of h, which has compact support. Okay, so now this, what am I doing now? I'm changing, here I'm writing in the spectral gap theorem, the perturbation theorem, the Nagaev theorem bit, like that. And now I change variables. Instead, I should go on to the whole real line. So I'm changing variables and getting an integrand which tends to 0 on a much larger domain of integration. And now I can see what's going on here. I mean, you see what's going on. These guys are going to 0. This is going to kappa. This is going to the Gaussian distribution. This is going to 0. So I get that this goes to 1 over 2 pi integral Fourier transform of Gauss and e to the I kappa x, which is, this comes out, this is the integral of h, and 1 over 2 pi, this is the Gaussian, this should be, maybe there should be a square root there. Anyway, in order to get something out of this, you define, this is Breiman's thing now, you define radon measures on R, you fix everything here. There's your radon measure. And so this is a radon measure on R, so it's a linear functional on continuous functions of compact support. I can choose my H so that it's strictly positive. And so what I've got is a condition for weak star convergence to this, to the Lebesgue measure weighted by e to the minus kappa squared divided by 2 times 1 over 2 pi. So that's basically Breiman's proof. And then what you have to do is feed in H to be the indicator function of I. And then you're finished. Okay, so that's it. I'm a little bit early. Here's some references I've got. So I guess what I'm going to do, I mean, you could just stare at, be impressed by the amount I had to prepare here. But what I'll do is I'll send the handout of this to the secretaries. They'll post it, and then if you want it, you can look at it. So that's on inner functions. This is on spectral gaps. Nothing new here. This is 1937. This is, this has been 1948. Somehow it didn't come out. And this is 72. And this is perturbations and local limit theorems. Okay, thank you for listening. SG, this 127 should be one of your birthdays. That's the idea.
Any questions? If not, let's thank the speaker again.